Welcome to the second generation of the CPIM product. This demonstration is going to deal with two main topics, the topics of convergence and virtualization. The success of convergence depends on the precision of the implementation and management thereof. While convergence contracts the footprint, it magnifies the effect of even the simplest of faults, demanding exact execution and management. Virtualization, on the other hand, is the future. However, in our lifetimes, it is unlikely that a virtual solution will ever run on virtual hardware. In order to capitalize on the investment and promise of virtualization, the link between the physical and the logical worlds must be established and well managed. If we've learned anything from the video game market, it's that 2D is not enough. The perspective is too narrow. The same is true for attempting to manage a multi-million-dollar capital investment as complicated as a data center. Today's data center requires an enterprise-wide holistic perspective that spans the traditional IT and operational silos, and as that data center converges, that perspective becomes essential. CPIM takes the visualization of your data center beyond the rack, beyond the row, and beyond the four walls of the traditional data center itself. In the visualization you are seeing, you have full spatial awareness. Everything that affects the business is in the model, and the relationship between all of the items of the business, owned by the business, operated by the business, is documented. You also have full context, and as you can see with the pop-up over the generator in the courtyard, you have full data to all of the objects within the view. Without the data, it's just pretty pictures. The model is also extendable and flexible. It's vendor agnostic, and the model, we believe, must enable be extendable to all types of assets. We term this dynamic visualization. There are no pre-canned images that rapidly become out of date, such as CAD, where you have changing configurations of rows or cabinets. We believe this to be the perfect marriage between data and graphics. These views are capable of displaying all aspects of the IT ecosystem. If we take off the outer top level floor, the second level floor, we can see into the data center. We can see the physical placement and physical security within the data center. Note the cages. We have full power data and connectivity in the circuit. We also have the cooling infrastructure, the network and the storage infrastructure, as well as the connectivity to all three. We provide a fluid interface with the capability to strip any element from the view. As you'll see now, we'll pull off the walls, we will pull out the tile grid, and finally the cabinets, giving you a better than real life perspective of your data center. What it also gives you is the ability to handle the data overload that is the modern data center. Data centers are extremely complex, and the solution to whatever problem you are prosecuting in the data center is to be found with relevant data that is relevant to your problem. This is where CPIM comes in. We're going to switch gears and talk about the power management of the data center. Here before you is a view of the entire infrastructure of this facility. We are going to isolate the facility down to the power, feeding in from the utility cabinet, which brings us in approximately 4,000 volts. We are going to then isolate this power infrastructure and strip everything out from the view that is not connected directly to the power infrastructure. Here we've done so. This facility is split into two A and B side power circuits across these two transformers. We're going to select one of the circuits, the B circuit. We're going to then isolate down just to the B circuit. As we rotate the view, you can see the connectivity in from the transformer into the ATS, which is fed by a UPS. The ATS then feeds the distribution panels, which then funnel out to the PDUs on the floor. As we zoom in, we'll continue our isolation by selecting a PDU, once again isolating the view to just the assets of the data center that are directly connected to that PDU, either upstream or down. As we rotate the view around again, we will strip off the doors of this PDU to expose the sub-panels, the breaker panels underneath. We select a breaker panel, and now we've isolated the entire view down to just the devices that are associated with that PDU breaker panel. We're going to continue this exercise down to the power strip level, and now we have exposed a device to utility virtual 3D model of the power infrastructure. Once again, end to end, from device all the way out to utility. Now we're going to walk back up the circuit, and we're going to show context data at each point. So we click on the server, we get a tooltip bar here, and draw your attention to the power values. We have nameplate power, which comes directly out of our templates. It's the manufacturer specifications. Every asset out of the database will populate with data. We then have a benchmark value. The benchmark value is basically a D-rating of that manufacturer specification. If you have a facility or a procedure set up where equipment comes into the loading dock, it goes on a test bench, and you meter that equipment, you can then take those readings, apply a percentage of D rating for all types for that asset across the data center in this benchmark draw field. Lastly, you see a draw. That is the monitored value. We have a monitored value of 0.7 kilowatts. All values that are monitored also historically track average and peak over time, and you can see in the dialog there that you've got the average draw is very, very close to 0.7 and the peak being 0.72. If we zoom in to the power supply, select it, and pull up its statistics, we can then see how much within this device, this particular side of the power is drawing. Here, the circuit draw is 0.07 kilowatts, which is 10% of the overall device draw. So it's basically a 90-10 situation where the other power supply draws 90% of the power. This power supply is the redundant power supply, draws 10. We're going to now click on the power strip. You can see the connectivity, the highlighted cable from device to power strip, and then we can bring up the statistics for the power strip. The power strip is drawing 3.39, which is 63% of its rating. And if we zoom a little bit out and over to the PDU, we can pick on that panel and get its statistics as it calculates. These values are calculated real time, running down the power circuit, collecting up the values. Here we have a circuit draw of 47.9, which is 20% of the rating capacity of this PDU. These monitored data points can be monitored for any portion of the power infrastructure circuit, so from device to utility. Next, we're going to introduce the link between the physical and the logical. As the image here changes, we've gone back to the top-down view of the entire physical infrastructure for the power infrastructure. We're now going to bring up a logical map. This map demonstrates the logical connectivity between the physical assets. Each one of the assets in the view has the same context that you saw before in the previous views, where you can select the item and bring up a context menu based on the device. Here we're going to do the utility cabinet again. There is its data. What this provides is the complete picture, because optimization, either in power or any other element in the data center, does not happen at the device or the PDU level. It happens at the enterprise level. Solutions for the business is about working smarter, not necessarily harder. The business value of proper power management is reducing cost, both for energy effectiveness and efficiency, aligning the business to regulatory constraints in order to adhere to become in compliance, or to maximize tax credits or other benefits from compliance. We're now going to walk through a series of use cases, the first one being analyzing risk, focusing on power redundancy. Business critical applications must have redundancy. However, redundancy by its nature is inefficient. The balance is to run only the most critical applications on your redundant hardware, but to do so you must be able to interrogate the redundancy level of your hardware. CPIM can simulate a failure of a power component. In this example, we're going to select a single PDU and we're going to simulate its failure. Highlighted in red are all the devices that completely lost power due to the outage. Highlighted in yellow are devices which survived the outage by switching to an alternate power source. we can extend this use case to multiple points of failure. We back up and we select another PDU. We can then simulate the failure on the pair, and once again the coloring scheme is exactly the same. Red devices completely lost power, yellow devices survived. I will call your attention to the upstream circuit from the PDU. All the devices in red upstream signify devices that could possibly have caused the PDU to go down if the failure was not localized to the PDU level. Up in the right hand corner you see the ATS is still yellow. It is so because the ATS has an alternate feed from the generator. The business relevancy of this use case is data center planning. Precise data center planning. The ability to not only on day one lay out your redundancy model and build your data center to that model, but also in days 2, 3, 4, and 5 to make sure that your redundancy model is maintained over time so that every new addition to the data center or subtraction from the data center adheres to the redundancy model. And then at later dates you can check to make sure the redundancy model has not been violated by unplanned or unscheduled changes. Fault recognition and recovery will be our next scenario. In this scenario, CPIM is fully integrated with a help desk system such as Remedy. In this case, the ticketing system has submitted tickets against servers when the users are reporting an outage. These tickets can be integrated into iTRACS, allowing CPIM to select the servers that are reported for outages, and then the IT professionals in the department can compute a root cause analysis. This analysis identifies in red all assets that are shared between the selected servers, not just power, but storage and network too. You get nearly an instant isolation of what the network, or what within the network may be causing the outage. Once the failed component is identified, here our suspicion is the Cisco switch in the back of this row. As we spin it around, once it's been identified, the IT department can go on the offensive by tracing the network connectivity out from the switch and identifying all servers and thus all applications running on those servers. IT can notify business units or customers of outages on those devices prior to the end user reporting the outage. The relevancy here, we're reducing operational costs, we're maximizing uptime, we're also doing an intangible, we're improving the SLA, the level of service that the IT department provides back to the business. We're giving them a perspective of a proactive department that can not only fix problems when they happen, but can also anticipate them and notify end users before the end user even recognizes that they have a problem. The next use case revolves around data center planning. Up to this point, we have been viewing the live environment at the current point in time. However, no data center is static. One can make the case that data centers are practically living organisms that evolve over time. A forward-thinking business needs to visualize that evolution. CPIM delivers by applying future scheduled changes within our work order system to the model, creating what we term a future view. As you can see across the bottom of the screen, there is a bar that denotes the point in time, the number of days out from now that is being displayed in the view. As we move the bar to the right, you can see assets appearing in the view, and not just servers, but their connectivity, both power and network, as well as cabinets in the adjacent row. In addition to this functionality, we can slide the bar back to the left. We can select on a switch in that first row, and we can isolate the future based on a single item. So here, everything has been removed from the view except for the switch itself, and we're going to then progress the bar to the right again to see what is the changes in connectivity to that switch over time, the planned connectivity. The value here, back to the business, precision planning, the ability to not react to changes in your data center, but to plan those changes, to know what the effect is prior to the equipment going in production environment so that you can help manage change with more confidence. Also provides the ability to what-if scenario. If this was a development area in your data center and you were testing out a new pod configuration, you could provision or commission all of the equipment into that pod, You can see its effect, its resource utilization, both in power, space, network, and storage, so that you can anticipate with much more clarity what a change will do to your production environment. Also, we have reportable resource utilization metrics for all the stated values, power, cooling, network, between not only in the present, but also at any point of the proposed future. Our last use case is going to deal with the virtual to physical link. In this case, the business needs to identify the hardware hosting virtual machines utilizing a virtual connect environment. So we're going to search for all assets in this data center that are running an application that we have termed Virtual Connect A. We run our search, and it returns to us a set of servers. Here they are in the browser control. We've now selected all of those servers, and we're going to compute that same analysis, root cause analysis over these servers. But in this case, we're not looking for a failure. We're simply looking for all of the assets within the data center that support these machines. Because when you look at it, yes, the physical machines that support the virtual environments are a single point of failure for those virtual environments. However, those physical machines are not standalone. They do not live by themselves in the data center. They are supported by a host of other assets. And this visual right here gives you full context into all the dependencies of those servers, and thus all of the physical dependencies of those virtual applications. The net value here is a converged IT stack, physical to logical, a converged collaborative enterprises, logistics talking to facilities, storage speaking with network, ops sharing information with apps. In the end, we get an agile data center capable of rapid change, executed with extreme confidence to deliver value back to the business at the speed of the market. Thank you for your time. We hope you've enjoyed this demonstration of the CPIM product.